Bismillah ar-Rahman ar-Rahim. We have integral x from 0 to 1 of the inverse tangent of x, log x over 1 plus or minus x squared, times the square of log 1 minus x squared over 1 plus x squared. The product in the numerator is divided by 1 plus x squared. Let's do the change of variables. Y equal to 2 times the inverse tangent of x. dy is 2 dx over 1 plus x squared. Y is 0 when x is 0. When x is 1, y is twice the inverse tangent of 1. That's pi over 2. Every x here and there is replaced by tan y over 2. The inverse tangent of x is y over 2. Dx over 1 plus x squared is dy over 2. 1 minus cosine y over sine y is 2 times the square of sine y over 2, divided by 2 sine y over 2 cosine y over 2. This is tan y over 2. If we square both sides and add 1, in the numerator we get sine squared y plus cosine squared y plus 1, that's 2, minus 2 cosine y. In the denominator we have the square of sine y. If this plus sign is changed to a minus sign, in the numerator we get the square of sine y minus 1 minus the square of cosine y plus 2 cosine y. Sine y squared is 1 minus cosine y squared. The numerator is equal to minus 2 cosine y squared plus 2 cosine y. That's 2 cosine y between brackets 1 minus cosine y. So this ratio here is this function of y divided by that one, that's cosine y. This part of the integrand is the square of the natural logarithm of cosine y. If we use the plus sign here, this ratio is 1 minus cosine y over sine y times sine y squared over 2 times 1 minus cosine y. We obtain sine y over 2. When we have the minus sign, this ratio is 1 minus cosine y over sine y times sine y squared over 2 cosine y times 1 minus cosine y. We get sine y over 2 times 1 over cosine y. This part of the integrand is log sine y over 2. When we have the plus sign, with the minus sign, we get log sine y over 2 minus log cosine y. With the plus sign, the integral of interest can be written in terms of these integrals. One of them is integral y from 0 to pi over 2 of y log sine y times the square of log cosine y. The other integral is y from 0 to pi over 2 of y times the square of log cosine y. If we have a minus sign rather than a plus sign, we need to evaluate a third integral, y from 0 to pi over 2 of y times the cube of log cosine y. To evaluate the integral of interest, we need to obtain these three integrals. We have previously obtained the Fourier series of log sine y and log cosine y. Y is between 0 and pi over 2. We can use these series representations to obtain the integral x from 0 to pi over 2 of x times log sine x or log cosine x. We just insert the series and integrate term by term. When the integrand is x log sine x, we get this integral x from 0 to pi over 2x times cosine 2vx, where v is a positive integer. This integral is equal to minus 1 plus cosine by v over 4v squared. Summation v from 1 to infinity of 1 over v cubed is zeta of 3. Summation v from 1 to infinity of minus 1 to the v minus 1 over v cubed is zeta of 3. We need to subtract double the sum of the reciprocals of the cubes of the positive even integers. That's 2 times 1 over 8 zeta of 3. This sum is equal to 3 zeta of 3 divided by 4. When sine is changed to cosine, we get an extra minus 1 to the v here. We have these two integrals from previous work. Now we have the four integrals x from 0 to pi over 2 of log sine x, log cosine x, x log sine x, and x log cosine x. We can also use these representations to evaluate the integral x from 0 to pi over 2 of log sine x times log cosine x. It is equal to pi times log2 squared over 2 minus pi cubed over 48. If the integrand has x squared, replace x by pi over 2 minus x. X squared becomes x squared plus pi squared over 4 minus pi x. The product of logarithms remains as is. Split the right-hand side into three integrals. This integral is exactly what we have on the left-hand side, so these two go away. This integral is equal to this value. We now have the integral x from 0 to pi over 2 of x log sine x log cosine x. It is this part times pi over 4. If this product is alpha beta is equal to 1/2 alpha squared plus 1/2 beta squared minus 1/2 alpha minus beta squared. The integrand can be written as x times the square of log sine x plus the square of log cosine x minus the square of log sine x minus log cosine x. Let's move to the integral of the square of log2 sine x. Log sine x is equal to minus log2 minus this sum here. So log2 sine x is minus this summation. We need to square. We obtain this double sum. Integrating term by term, we need to evaluate the integral x from 0 to pi over 2 of cosine 2vx times cosine 2kx. K and v are positive integers. When k is not equal to v, this integral is 0. If k is equal to v, we get pi over 4. So this double sum is summation v from 1 to infinity, pi over 4, 1 over v squared. That's pi over 4 times pi squared over 6. Log2 sine x is log sine x plus log2. Expand the square. When we integrate this part, we get pi over 2 log2 squared. When we integrate that one, we get minus pi log2 squared. We also have the integral of the square of log sine x. This integral is pi cubed over 24 plus pi over 2 log2 squared. By changing x here to pi over 2 minus x, we get the integral of the square of log cosine x. We have these integrals from the previous page. What about the integral of the square of log 2 sine x times x? We use the Fourier series and interchange the order of integration and summation. We have this double sum. When k is equal to v, the integral is pi squared over 16. The double sum becomes summation v from 1 to infinity, pi squared over 16 times 1 over v squared. That's pi squared over 16 times zeta of 2. We get pi to the power 4 over 96. The situation is more complicated when k is not equal to v. Let's consider this part of the solution, 1 over k plus v squared. To obtain this double sum, multiply numerator and denominator by v plus k. The summand becomes v plus k over vk times v plus k cubed. V plus k over vk is 1 over v plus 1 over k. We have summation v from 1 to infinity, summation k from 1 to infinity, 1 over v times 1 over v plus k cubed. When k is 1, this is 1 over v plus 1 cubed. When k is 2, this is 1 over v plus 2 cubed, and so forth. We can rewrite this double sum as summation v from 1 to infinity, summation k from v plus 1 to infinity, 1 over v times 1 over k cubed. We get the exact same value if this 1 over v is replaced by 1 over k. This double sum is equal to 2 times the double sum v from 1 to infinity, k from v plus 1 to infinity of 1 over v times 1 over k cubed. Interchange the order of summation. We have summation k from 2 to infinity, v from 1 to k minus 1. Because k is strictly greater than v, the summation with respect to v is the harmonic number h of k minus 1, which can be written as h of k minus 1 over k. So the double sum is equal to 2 times summation over positive integer k of hk over k cubed. Hk is the kth harmonic number, 1 plus 1 half plus 1/3 all the way to 1 over k. We also have minus 2 zeta of 4. Zeta of 4 is pi to the power 4 over 90. Now reconsider the double sum with this extra factor, minus 1 to the power k plus v. Same trick, multiply upstairs and downstairs by v plus k. Write v plus k over vk as 1 over v plus 1 over k. As we did here, replace k by k minus v. Swap the order of summation. The sum with respect to v is hk minus 1 over k. We get this harmonic sum, but with minus 1 to the power k. This sum is minus zeta of 4 times 1 minus 2 over 16. When we multiply by minus 2, we get 7 pi to the power 4 over 360. We need to repeat these steps, replacing k plus v by k minus v. Due to symmetry, the summation v from 1 to infinity, summation k from 1 to infinity, k not equal to v, is equal to double summation over positive integer v, k from v plus 1 to infinity. Replace k by k plus v. K becomes from 1 to infinity. The product kv times k minus v squared is replaced by vk squared times k plus v. 1 over v times k plus v is equal to 1 over k between brackets 1 over v minus 1 over k plus v. Interchange the order of summation. Summation v from 1 to infinity, 1 over v minus 1 over k plus v. This is 1 over 1 minus 1 over k plus 1, plus 1 over 2 minus 1 over k plus 2, all the way to 1 over k minus 1 over k plus k. Then we get 1 over k plus 1 minus 1 over k plus 2, and so on. We get cancellations. The remaining terms are hk. So this double sum is twice this harmonic sum. When we do the same steps with this extra minus 1 to the v plus k, we get this result. We can write down this integral in terms of these harmonic sums obtained in previous videos. Knowing the integral with log 2 sine x, we can obtain the integral with log sine x. We have this integral. We can obtain this one by replacing x by pi over 2 minus x. Integral x from 0 to pi over 2 of x times the square of log cosine x is equal to pi over 2 integral x from 0 to pi over 2 of the square of log sine x minus integral x from 0 to pi over 2 of x times the square of log sine x. Both integrals are on the previous page, and this one is also here. This integral is one of the 3 integrals we need to evaluate. The other 2 are integral x from 0 to pi over 2 of x times the cube of log cosine x and integral x from 0 to pi over 2 of x times log sine x times the square of log cosine x. We can evaluate these 2 integrals via developing a series representation for the cube of log 2 cosine x. This is our next task. 1 minus x over 1 minus x is 1. Multiply both sides by an x to the n and sum over positive integer n. On the right hand side, we get 1 over 1 minus x times the difference between these two sums. Summation n from 1 to infinity of an x to the n. Here we have summation m from 1 to infinity am x to the m plus 1. We have plus 1 here because of this x. If m plus 1 is equal to n, we can rewrite this sum as summation n from 2 to infinity of an minus 1 x to the n. If a0 is equal to 0, we can start this sum at 1. We can then combine these two sums. The result we obtain is that summation n from 1 to infinity an x to the n is equal to 1 over 1 minus x summation n from 1 to infinity an minus 1 times x to the power n. Let's employ this result. For an, we use the square of the nth harmonic number minus the generalized harmonic number of order 2. This is summation k from 1 to n, 1 over k squared. Here is an minus 1. These two terms are equal to minus 1 over n squared. Hn squared minus hn minus 1 squared is hn minus 1 times hn plus hn minus 1. This difference is equal to 1 over n. The sum is equal to 2hn minus 1 over n. So this bracket is 2hn over n minus 1 over n squared minus 1 over n squared, that's minus 2 over n squared. This sum, or generating function, is equal to 2 over 1 minus x summation over positive integer n of hn x to the n over n minus 2 over 1 minus x summation over positive integer n of x to the n over n squared. This sum here is the logarithm of x. What about this sum? We have this previous result. Rewrite x as y and divide both sides by y. Integrate both sides from 0 to x. On the left hand side, we get the sum we are interested in. On the right hand side, we get integral y from 0 to x of minus log 1 minus y over y times 1 minus y. 1 over y times 1 minus y is equal to 1 over y plus 1 over 1 minus y. Split into two integrals. This one is the logarithm of x. That one is 1/2 times the square of log 1 minus x. Moving the logarithm function to the other side, this bracket is equal to 1/2 log 1 minus x squared. In this sum, change n to n minus 1. We have summation n from 2 to infinity hn minus 1 squared minus hn minus 1. This bracket is multiplied by x to the power n minus 1. We can start this summation at 1. This sum is equal to the square of log 1 minus x over 1 minus x. Multiplying both sides by x, we get this result here. Consider the same difference, but multiplied by e to the I to n x over n times minus 1 to the n. We can write 1 over n as integral y from 0 to 1 of y to the n minus 1. Interchange the order of summation and integration. Y to the n minus 1 is y to the n divided by y. This bracket is multiplied by minus y e to the power I to x, all raised to the power n. We can obtain this sum from here by replacing x by minus y e to the I to x. After simplifying, we get this integral with respect to y. It is equal to minus 1/3 times the cube of log 1 plus e to the I to x. The next step is to take the real part of each side. On the left-hand side, this term is replaced by cosine 2nx. The real part of the right-hand side is minus 1 over 6, the cube of log 1 plus e to the I to x, plus the cube of log 1 plus e to the minus I to x. If this logarithm is alpha, and that is beta, alpha cubed plus beta cubed is equal to alpha plus beta cubed minus 3 alpha beta times alpha plus beta. Alpha plus beta is log the product of these two brackets, which is 2 plus 2 cosine 2x. This is equal to log 4 times the square of cosine x, which is 2 log 2 cosine x. This is alpha plus beta. What about alpha beta? We have log 1 plus e to the I to x times log 1 plus e to the minus I to x. This is log e to the ix, e to the minus ix plus e to the ix, log e to the minus ix, e to the ix plus e to the minus ix. This logarithm is ix plus log 2 cosine x. This logarithm is minus ix plus log 2 cosine x. This product is x squared plus the square of log 2 cosine x. This is alpha beta. This is alpha plus beta. We can use this to write down the sum of these two cubes. It is equal to minus 6x squared log 2 cosine x plus 2 log 2 cosine x cubed. We have that summation n from 1 to infinity, this difference, times cosine 2nx over n times minus 1 to the power n. This is equal to x squared log 2 cosine x minus 1 over 3 log 2 cosine x cubed. Now we have a series representation for this logarithm. It is equal to 3x squared log 2 cosine x minus 3 times this sum. Integrate both sides from 0 to pi over 2. we have integral x from 0 to pi over 2, the cube of log 2 cosine x equal to the integral of x from 0 to pi over 2 of 3x squared log 2 cosine x. Integrating term by term, we obtain minus 3 summation n from 1 to infinity, this bracket, times minus 1 to the power n over n, integral x from 0 to pi over 2 cosine 2nx. This integral is 0 for every positive integer n. These two integrals are equal. We know from the second page that this logarithm is minus summation v from 1 to infinity, minus 1 to the v cosine 2vx over v. We can do term by term integration. The right hand side is minus 3 pi over 4 summation v from 1 to infinity 1 over v cubed. This sum is zeta of 3. So this integral is minus 3 pi zeta of 3 over 4. We are interested in this integral and we have this identity. We multiply both sides by x and integrate from 0 to pi over 2. Regarding the series, we do term by term integration. When this part is multiplied by x, x squared becomes x cubed. Log 2 cosine x is summation over positive integer v of minus 1 to the v cosine 2vx over v. Swap the order of integration and summation. We have this integral x from 0 to pi over 2 of x cubed cosine 2vx. It is given by this bracket. We obtain a result in terms of zeta of 3 and zeta of 5. This integral is cosine by n minus 1 over 4n squared. We need to evaluate this sum. Also the sum with the extra term minus 1 to the power n. 1 over n cubed is 1/2 integral x from 0 to 1 of x to the n minus 1 times the square of log x. Recall that integral x from 0 to 1 x to the a log x to the power b is minus 1 to the b gamma of b plus 1 over a plus 1 to the power b plus 1. This is a special case. So we use this integral representation for 1 over n cubed. Then we interchange the order of operations. The sum is equal to the square of log 1 minus x over 1 minus x. This integral is minus 1 over 6 integral x from 0 to 1 of log x squared d log 1 minus x cubed. We do integration by parts. This is minus 1 over 6, limit as x tends to 1 from below, of log x squared log 1 minus x cubed, plus 1 over 6, limit as x tends to 0 from above, of log x squared log 1 minus x cubed. These two limits are 0. We also have 1 over 6 integral x from 0 to 1, the cube of log 1 minus x, multiplied by the derivative of this function of x, which is 2 log x over x. We obtain 1 over 3 integral x from 0 to 1 of log 1 minus x cubed times log x over x. Change x to 1 minus x. We get 1/3 integral x from 0 to 1, the cube of log x log 1 minus x over 1 minus x. In a previous video, we obtained the integral x from 0 to 1 log x to the power k, where k is a positive integer, log 1 minus x over 1 minus x. When k is equal to 3, we get 12 zeta of 5 minus 6 zeta of 2 times zeta of 3. Dividing by 3, we find that this sum is equal to 4 zeta of 5 minus pi squared zeta of 3 over 3. If we have an extra minus 1 to the power n, we start with the same step of writing 1 over n cubed using this integral. Then we interchange the order of integration and summation. When we do the sum, we get 1 plus x rather than 1 minus x. We get minus 1 over 6 integral x from 0 to 1, the square of log x d, the cube of log 1 plus x. We do integration by parts again. We get limits that are equal to 0, and we get this integral multiplied by 1 over 3. Our focus now is integral x from 0 to 1 of log 1 plus x cubed log x over x. We employ the substitution x equal to 1 minus y over y, which means that y is 1 over 1 plus x. dx is equal to minus dy over y squared. When x is 1, y is 1/2. When x is 0, y is 1. 1 plus x is equal to 1 over y. So the cube of log 1 plus x becomes minus the cube of log y. Log x is log y minus log 1 minus y. 1 over y times 1 minus y is 1 over y plus 1 over 1 minus y. The integrand has the product of log y minus log 1 minus y in one bracket. A second bracket contains 1 over y plus 1 over 1 minus y. We multiply and split into 4 integrals. The antiderivative of log y to the power 4 over y is 1 over 5 log y to the power 5. Using the limits of integration, this integral is log 2 to the power 5 over 5. The integral y from 1/2 to 1 of log y to the power 4 over 1 minus y can be written as the difference between two integrals. An integral from 0 to 1 minus an integral from 0 to 1/2. To evaluate this integral, we can write integral y from 0 to 1 log y to the power 4 summation over non-negative integer g of y to the power g. Integrating term by term, we have summation j from 0 to infinity, integral y from 0 to 1 log y to the power 4 y to the j. We can use this result. This integral is equal to minus 1 to the power 4, that's 1, times gamma of 5, which is 4 factorial, that's 24, divided by j plus 1 to the power 5. This is 24 zeta of 5. This integral is also written as an integral from 0 to 1 minus an integral from 0 to 1/2. In the integral from 0 to 1/2, replace y by 1 minus y. This part is minus 1 over 4, integral y from 1/2 to 1, log 1 minus y d log y to the power 4. Doing integration by parts, we get minus log 2 to the power 5 over 4, minus 1 over 4, integral y from 1/2 to 1 of log y to the power 4 over 1 minus y. This is equal to minus log 2 to the power 5 over 4, minus 1 over 4. The integral from 0 to 1, we have just obtained it. It is equal to 24 zeta of 5. So we have here 6 zeta of 5. Then we have plus 1 over 4, integral y from 0 to 1/2 of log y to the power 4 over 1 minus y. This integral can be combined with this one as minus 3 over 4 times the integral. We can also combine these two terms with these two. We need to obtain this integral. It is equal to 3 times this sum. We need the sum to evaluate this integral. We know this integral. We need now to obtain that one. Consider positive integer m and the integral x from 0 to 1/2 log x to the power m over 1 minus x. This is integral x from 0 to 1/2 log x to the power m summation g from 0 to infinity x to the g. Interchange the order of integration and summation. Do the change of variables x equal to t over 2. When x is 1/2, t is 1. X to the g is 1 over 2 to the j times t to the j. Log x is log t over 2, which is log t minus log 2. This bracket is raised to the power m. Dx is 1/2 dt. This bracket to the power m is equal to summation k from 0 to m choose k minus log 2 to the power m minus k log t to the power k. There is this t to the power j, so we have integral t from 0 to 1 t to the power j log t to the power k. This integral is minus 1 to the power k gamma of k plus 1, which is k factorial. Downstairs we have j plus 1 to the power k plus 1. Let's sum first over j. We have summation k from 0 to m choose k minus log 2 to the power m minus k minus 1 to the k factorial. Summation g from 0 to infinity 1/2 to the power j plus 1 over j plus 1 to the power k plus 1. This is a polylogarithm function. We now have this integral. We need the special case when m is equal to 4. Here is what we get. Note that we need the dilogarithm of 1/2 and the trilogarithm of 1/2. Both values were previously obtained and are included in the appendix. We still have to tackle this integral. Here it is multiplied by 4. We make use of this identity. Alpha is log 1 minus x and beta is log x. We split into 5 integrals. This one is straightforward. In that one, replace x by 1 minus x. For this integral, use the substitution y equal to 1 minus x over x, which means that x is 1 over 1 plus y. When x is 1/2, y is 1. When x is 1, y is 0. We obtain this integral. Rename y as x. When the magnitude of x is less than 1, 1 over 1 plus x is summation j from 0 to infinity, minus 1 to the j, x to the j. Integrate term by term. We obtain a result in terms of zeta of 5. For these two integrals, we do integration by parts. Replace x here by 1 minus x. Rewrite that integral as an integral from 0 to 1 minus an integral from 0 to 1/2. This part is minus 24 zeta of 5. These two integrals are here. Back to this integral. When x is replaced by 1 minus x, we get an integral from 0 to 1/2. Rewrite as an integral from 0 to 1 minus an integral from 1/2 to 1. This integral is exactly the one on the left-hand side. So we have 8 integral from 1/2 to 1. The cube of log 1 minus x log x over x is equal to 2 integral from 0 to 1/2 log x to the power 4 over 1 minus x. Change x to 1 minus x. So we have here plus 4 integral x from 0 to 1 log x cubed log 1 minus x over 1 minus x. We know these two integrals. We also have these terms. Now we know this. Consequently, we have this sum and this integral. Here it is. We can also obtain the integral with sine rather than cosine by changing x to pi over 2 minus x. This is what we get. Using the facts that log 2 cosine x is log cosine x plus log 2, log 2 sine x is log sine x plus log 2, we can use these two integrals and other results we have obtained to obtain the integrals without these twos. To summarize what is going on, our main interest is this integral. On the first page, we have discovered that to evaluate this integral, we need three integrals. We have obtained these two. We need now to turn our focus on the third integral, x from 0 to pi over 2, x log sine x times the square of log cosine x. We have integral x from 0 to pi over 2 of the square of log sine x times log cosine x. Log sine x is minus log2 minus this summation, split into two integrals. This one is on the third page. We use a previously derived series representation for log sine x, log cosine x. We interchange the order of summation and integration. With positive integers n and m, integral x from 0 to pi over 2 cosine 2nx times the square of sine 2mx is minus pi over 8 if n is equal to 2m. Otherwise, this is 0. We can rewrite this double sum as a single sum over positive integer m. This n is replaced by 2m. Split into two sums. This is zeta of 3. When this series was derived, we also got an integral representation for this bracket. Swap summation and integration. This sum is equal to the dilogarithm of x squared. Integral x from 0 to 1 of the dilogarithm of x squared over 1 plus x is integral x from 0 to 1 of the dilogarithm of x squared d log 1 plus x. Do integration by parts. We obtain log 2 times the dilogarithm of 1, which is zeta of 2 or pi squared over 6, minus integral x from 0 to 1 of log 1 plus x times the derivative of this function of x. The dilogarithm of x squared is minus integral from 0 to x squared log 1 minus u over u. The first derivative of this function of x with respect to x is minus 2x log 1 minus x squared over x squared. This is minus 2 log 1 minus x squared divided by x. Log 1 minus x squared is log 1 minus x plus log 1 plus x split into two integrals. Using this result, we obtain these two integrals. This integral is pi squared log 2 over 6 minus 3 zeta of 3 over 4. We now have this one. Changing x to pi over 2 minus x, we obtain its twin. What we are interested in is an integral with this integrand times x. Consider integral x from 0 to pi over 2 x times log sine x squared log cosine x plus integral x from 0 to pi over 2 x log cosine x squared times log sine x. In this integral, replace x by pi over 2 minus x. The sum of these two integrals is pi over 2 times this integral. Integral x from 0 to pi over 2 of x times the cube of log sine x cosine x. Write down log sine x cosine x as log sine x plus log cosine x. Expand. We have these two and the sum. Take this integral, multiplied by 6. Use this identity. Alpha is log cosine x. Beta is log sine x. Alpha plus beta is log sine x cosine x. Alpha minus beta is minus log 10x. This one is here. We also know that one. What remains is integral x from 0 to pi over 2 x times the cube of log 10x. Make the substitution y equal to 10x. When x is 0, y is 0. When x tends to pi over 2, y tends to infinity. X is the inverse tangent of y. This part becomes the cube of log y. Dx is dy over 1 plus y squared. We are done once we evaluate this integral. We will need this identity involving the polylogarithm function of order 4. Start with the dilogarithm of minus 1 over y. That's integral u from 0 to minus 1 over y of minus log 1 minus u over u. The first derivative with respect to y is 1 over y squared minus log 1 plus 1 over y over minus 1 over y. This is log 1 plus 1 over y over y. This is log 1 plus y minus log y. Integrate this side and that one from x to 1. On the left-hand side, we get the dilogarithm of minus 1 minus the dilogarithm of minus 1 over x. Integral y from 0 to 1 of log y over y is 1/2 times the square of log x. We also have this integral. Do the change of variables, y equal to minus z. This part is the dilogarithm of minus x minus the dilogarithm of minus 1. Minus the dilogarithm of minus 1 is pi squared over 12. Using this side and that one, the dilogarithm of minus x plus the dilogarithm of minus 1 over x is equal to twice the dilogarithm of minus 1, that's minus pi squared over 6, minus 1/2 log x squared. Rewrite this identity using variable u, divide by u, then integrate from x to 1. From here we get pi squared log x over 6 plus log x cubed over 6. We also get these integrals. Using these substitutions, we can rewrite both integrals in terms of the trilogarithm function. We get this identity. Note that these two terms go away. Like above, replace x by u, divide by u, and integrate from x to 1. Using these substitutions, we obtain integrals that can be represented using the polylogarithm function of order 4. This is the identity that we need. Let's go back to our integral. Write the inverse tangent of x as integral y from 0 to 1 of x over 1 plus x squared y squared. Interchange the order of integration. The integral with respect to x is over positive x of x times the cube of log x over 1 plus x squared 1 plus x squared y squared. Do the change of variables, alpha equal to x squared. This is the integrand in terms of alpha. Split the integral into an integral where alpha is between 0 and 1 and another where alpha is greater than 1. Change alpha to 1 over alpha. We get another integral from 0 to 1. Combine the two integrals and do partial fractions. The polylogarithm function of order n plus 1 has the following integral representation: minus 1 to the power n over n factorial, integral t from 0 to 1 of x log t to the power n over 1 minus xt. We have log alpha cubed here, so we can express this integral in terms of the polylogarithm function of order 4. The value of this integral as a function of y is given by this. Now we can employ the identity that we have just obtained. This bracket is equal to minus log y squared to the power 4 over 24 minus pi squared log y squared over 12. The integral of interest is the integral of this function over y from 0 to 1. We obtain the value of this integral in terms of zeta of 3 and zeta of 5. Since we have this integral, we can obtain that one. From this relation, we obtain our target. Knowing this integral and the two integrals x from 0 to pi over 2, x log cosine x squared and cubed, we obtain the integrals of interest.